we'll use the limit definition of the derivative to find f prime of x. So let's first write down the limit definition. So f prime of x is limit f of x plus h minus f of x divided by h as h approaches 0. So this is the starting point. First write this down. Now you know what you need. You need to plug in f of x plus h. So we already have f of x. So f of x is given to us. Let's try to figure out what f of x plus h is. So what is f of x plus h? In the function f of x, which is equal to radical 2x plus 3, everywhere you see an x, just replace it with x plus h. So this is equal to radical 2x plus 2h plus 3. So let's plug in the numbers now. So limit, keep writing limit until the end when you actually plug in the limit at some point. So that's square root of 2x plus 2h plus 3 minus radical 2x plus 3 whole divided by h. Now think about it. If we had to find limits, the first thing that we would do is substitute h equals 0. So that's our first step. This is what we need to try. But think about it. If you substitute h equals 0, clearly the denominator is 0. In the numerator, the 2h is going to become 0. So you have radical 2x plus 3 minus radical 2x plus 3, which is equal to 0. So what we have is a 0 over 0 form. So now we need to do something with this expression. So eventually what we want to do is be able to cancel a factor of h in the numerator with the h in the denominator. So we get rid of the 0 in the denominator, and then we try substituting h equals 0 once again. Now with radical expressions, if we have a 0 over 0 form, there's one thing that we could do, and that is multiply the numerator and denominator with the rationalizing factor of radical 2x plus 2h plus 3 minus radical 2x plus 3. So what's the rationalizing factor? So here we are. The rationalizing factor is, do you see a minus here? Everything remains identical except that we change the minus to a plus. So that becomes a plus radical 2x plus 3. We have to do the exact same thing in the denominator. Radical 2x plus 2h plus 3 plus radical 2x plus 3. And then of course we already have an h in the denominator, which needs to go eventually, and that's the reason why we are doing this. Now this is called a rationalizing factor because eventually, if you have like an a plus b times a minus b, you're going to get a difference of squares, a squared minus b squared. Notice the pattern, a plus here and a minus here. Everything else is identical. So a plus b times a minus b, if we take the product, it's equal to a difference of squares, which is a squared minus b squared. When we square each term, so this is our a and that's our b, this is our a and that's our b. So if we square the a and the b, clearly the radical expression is going to disappear, and instead of a radical expression we are going to have, let's see what we have, limit as h approaches 0, square the first 2x plus 2h plus 3 minus square the second, which is radical 2x plus 3, divided by, write down everything just the way it is, 2x plus 2h plus 3 plus radical 2x plus 3. So this is equal to Now notice that this is called a rationalizing factor for a reason. So right now we have a radical expression. It's going to become a rational expression. So we have limit as h approaches 0. We're going to lose the radical expression because the square cancels off with the radical sign, and we're left with 2x plus 2h plus 3 minus, in parentheses, don't forget the parentheses, 2x plus 3. The whole divided by, we repeat the same thing, radical 2x plus 2h plus 3. Put a radical expression, it's right across here, plus the radical sign goes right over 2x plus 3. So now we try to cancel anything we can. So notice that we have a 2x minus a 2x, a plus 3 minus a plus 3. So now we're left with limit as h approaches 0, 2h divided by h, and of course we still have 2x plus 2h plus 3 plus radical 2x plus 3. Now we're ready to cancel the h with the h, and now we do not have a 0 in the denominator. Remember, h was the one that was causing the 0 in the denominator. So now in order to find limits, we plug in h equals 0. So we have 2 in the numerator because the h got cancelled, and I'm going to plug in 0 for h. So 2 times 0 plus 3 plus radical 2x plus 3. So that is equal to 2 over radical 2x plus 3 plus radical 2x plus 3. That is equal to 2 over, we have 2 of the same type, and remember we are adding them together. So it's 2 of those, and it's 2 of radical 2x plus 3. The 2's get cancelled, and we have a 1 in the numerator and radical 2x plus 3 in the denominator. So this is f prime of x. So what we have so far is that we've used the limit definition of the derivative to find the derivative of radical 2x plus 3, and that is equal to 1 over radical 2x plus 3. Now, if we have to find, let's look at the second part, which says find f prime of x at x equals 1. So we know what f prime of x is. Now we need to evaluate f prime of x at x equals 1. So now all we have to do is plug in x equals 1. So that is 1 over radical 2 times 1 plus 3, which is equal to 1 over radical 5. So what we've done is we've evaluated the derivative at 1. So we first found the derivative. We can plug in any number as long as it's a valid number. As long as we have a valid answer, we can plug in any number and basically evaluate the derivative at any value for x. So now what we have is f prime of 1 is equal to 1 over radical x. So this is the slope of the tangent line at x equals 1. So now if we had to write down the equation of the tangent line, this is how we would do it. Y minus y1 equals m times x minus x1. So m is the derivative at that specific point, which is 1. All we have to do is evaluate y1. So now what is that? So f of x is equal to radical 2x plus 1. So f of 1, we are trying to find the y at x equals 1. So that would be y1. We plug it into the original function, not the derivative, remember, because it's a point on the actual function that we're trying to evaluate. So 1 plus 1, which is radical 3. So y minus radical 3 is equal to 1 over radical 5 times x minus 1.